Hello everyone, welcome back to the lecture series of PECD. Now, today we will discussing about the synchronous motor drives part 1. Before starting this session, I would like to inform you that after watching this video, you will be understanding about the basic principle of synchronous motor and their types of synchronous motors and the brief description about the cylindrical rotor wound field synchronous motor. So let us will start as you all know about the synchronous motor. The synchronous motor is construction wise same as an alternator and it runs at synchronous speed or it remains standstill. The speed can be varied by varying the supply frequency. So therefore, because the formula for synchronous speed is, we know that the ns equals to 120 f by p, where f is the supply frequency and p is the number of poles. Due to the unavailability of economical variable frequency sources, this method of speed control was not used in past and they were mainly used for constant speed applications. But the development of semiconductor variable frequency sources such as inverter and cycloconverter allowed the use of synchronous motor in variable speed applications. That means by developing the power electronics converter, the synchronous motor now used as a variable speed applications. So therefore the synchronous motor is not self-starting. It has to be run up to near synchronous speed by some means and it can be synchronized to the supply. The starting methods of synchronous motors are, one is by using an auxiliary motor and second one is by using the damper winding. The three-phase AC supply is connected to the stator, that means armature winding, and external DC source is given to the rotor field. So this is the about basic concept of synchronous motors. Now we will discussing about the types of synchronous motor. According to that, synchronous motor is mainly classified in 4 types. First one is wound field motor, second one is permanent magnet motor, third one is synchronous reluctance motor, and fourth one is hysteresis motor. The wound field synchronous motor is also classified in 2 types. One is cylindrical rotor type motor and second one is salient pole type of rotor. But now in our today's lecture we will discuss only the cylindrical rotor type wound field synchronous motor. As you observed in this slide, the cross sectional view of synchronous motor, in this figure you have observed the stator and rotor and their windings, how it is constructed. Now first we will discussing about the cylindrical rotor wound field synchronous motor. So how it is constructed? So I am deriving here, I am construct here the cylindrical rotor. This is the conductor. As you assume that this is not, this is the looking like as a cylindrical type. I just explained here. So according to cylindrical rotor type wound field synchronous motor, in which the air gap is uniform, so we have the flux produced by the rotor, and this type of rotor, the windings are placed in the rotor and the stator is surrounding the rotor, and just the rotor is cylindrical, so therefore it is called the cylindrical rotor wound field synchronous motor, and it is used for higher speed applications. The wound field synchronous motor is generally used for very high power applications in the range of megawatt. So this is the basic construction of cylindrical rotor type wound field synchronous motor. Now we will discussing about the working principle of cylindrical rotor wound field synchronous motor. According to that, the rotor is provided with DC field winding and damper winding. The stator contains three-phase winding and it is connected to the AC supply. When a three-phase AC supply is given to the stator, a rotating magnetic field revolving at a synchronous speed is produced, and the DC excitation in rotor produces a field. This field interacts with rotating magnetic field to produce a torque which is in pulsating in nature. As a result, synchronous motor is not self-starting. Normally the motor is made self-starting by providing the damper winding on the rotor side. Due to the presence of damper winding, the motor will start as an induction motor. And now when speed of motor reaches to near the synchronous speed, the DC excitation is given to the rotor. Now the rotor poles get locked with rotating magnetic field poles in the stator and continue to rotate at the synchronous speed. So therefore it is called synchronous motor. Now this is about the load angle, power angle, or we can say the torque angle. The rotor poles, as we know that the rotor poles are locked with the stator poles and both run at synchronous speed in the same direction. As load on motor increases, the rotor tends to fall back in the phase by some angle. That means as load is increases, so therefore the rotor has fall back in phase by some angle, and this angle is known as load angle and it is denoted by the del, and the value of del is depends on the load. As you seen in this figure, the stator pole and rotor pole, how it is fall back in phases by some angle. There is some phase difference between stator and rotor. So this is the torque angle. Now this is the cylindrical rotor wound field synchronous motor, in which the cylindrical rotor machine has its rotor in cylindrical form with a distributed DC field winding embedded in the rotor slots. As you seen in this circuit, this is the schematic diagram of the cylindrical rotor wound field synchronous motor. Now we will draw the equivalent circuits. Simplified per phase equivalent circuit of cylindrical rotor synchronous motor is shown in this figure. According to that, there is axis, that is the synchronous reactance, and this is the induced EMF, and this is the voltage, and E is known as induced EMF or excitation EMF. From this circuit, the input power to the motor is given by these equations, that is the P input equals to 3VIS cos phi, that is our first equations. In these equations, where phi is the phase angle of current and voltage. So according to these equations, as we assume that the stator losses has neglected, and since the armature loss has been neglected, this is also the air gap power, as no power is transferred to the rotor circuit. All of the air gap power is converted into the mechanical power, hence there is no any loss, all losses are neglected. Then the input power is given that mechanical power, and this power is given by Pm by this equation, that is the Pm equals to 3VIS cos phi, and this is our second equation. According to the equivalent circuits, we have find out the value of Is. So according to that, the Is equals to V angle 0 minus E angle minus delta divided by J of xs. Now we can write these equations equals to V upon xs angle minus pi by 2 minus E upon xs angle minus del plus pi by 2, and if we are consider the real parts, the Is cos phi equals to V upon xs cos minus pi by 2 minus E upon xs cos minus del minus pi by 2. Now the resultant, that will be E upon xs sin del. This is the our third equations. Now substituting these value in equation number 2, and we will getting the Pm equals to 3V upon xs sin del. So this will be our the fourth equations. The rotating field produced by the stator moves at a synchronous speed, and which is given by omega ms equals to 4 pi f divided by p in radian per second. This is our fifth equations, where f is the supply frequency and p is the number of poles. So for steady torque to be produced, the rotor field must move at the same synchronous speed as stator field. Since rotor field has same speed as that of the rotor also run at synchronous speed. So therefore the torque is given, that the formula for torque is that T equals to Pm upon omega m. Now we can write this formula in this type of equation, that is the 3 VE divided by xs omega s sin del. This is our sixth equation. So this is our torque equations. Now we will draw the torque speed characteristic. So according to that, for a given field excitation, the E is constant. So therefore mechanical power and torque are proportional to the del, and this del is called torque angle or power angle, as we studied in previous slide. So according to this speed torque characteristic, as you observed in this figure, the graph is plotted between speed and torque. Here speed is constant because this is a synchronous motor, and according to that, if we draw the characteristic, so this will be the first quadrant, this is the second quadrant. So according to that, this is the speed is constant and this is the pull out torque. We know that this is the pull out torque, or we can say this is the maximum torque. When it will comes to the maximum torque, the this is the motoring region and this is the braking region. The motoring region or motoring torque is obtained when del is positive and E lags behind the V, and whereas the generative braking is obtained when del is negative or E leads the V voltage. And in this speed torque characteristic, you observe that, so this is the pull out torque in motoring region and this is the pull out torque in the braking region. So beyond this value, the synchronous motor gets their synchronism. That means after that, this is the value of maximum torque and this is the constant speed, and this is what is called the synchronous speed. The regenerative braking will get when the del is negative, and you know that we will getting the maximum torque when del equals to 90 degree. If it is plus 90 degree, then that will be motoring torque, and if we are getting the minus 90 degree, it will be the braking torque. As we know that the maximum torque Tmax or pull out torque is reached at del equals to plus minus 90 degree. If the load torque exceeds Tmax or pull out torque, the machine pull out of synchronism according to this speed torque characteristic. Now we are discussing about the advantages of synchronous motor. First, one of the major advantages of synchronous motor is the ability to control the power factor. In synchronous motor, the speed remains constant irrespective of loads. Second one, this helps in industrial drives where constant speed is required irrespective of the load is driving. Third one is the synchronous motor can be constructed with wider air gaps than induction motor, which makes these motors mechanically more suitable. Next one is, in synchronous motor, the electromagnetic power varies linearly with the voltage. And last one is that the synchronous motor usually operate with higher efficiency, that means more than 90 degree, especially in low speed and unity power factor applications compared to the induction motor. Now there are some disadvantages of synchronous motor. That is the first, synchronous motor cannot be started on the load, that means its starting torque is 0. Second one is, when loading on the synchronous motor increases beyond its capability, the synchronism between rotor and stator rotating magnetic field is lost and motor comes to halt. Next one is, the synchronous motor requires DC excitation which must be supplied from the external sources, and synchronous motor are inherently not self-starting motors. And last one is, the synchronous motors cannot be used for variable speed applications. So these are the some disadvantages of synchronous motor. Now this is the whole about the description about the cylindrical rotor wound field synchronous motor. Now in next lecture we will discussing about the salient pole rotor wound field synchronous motor. Thank you.